We are going to continue looking at graphing linear inequalities and how it relates to problem solving. And again, linear inequalities, what they do is represent all of the possible solutions to a particular scenario, which is very useful, and we can do that on a sheet of graph paper. In the previous example, we looked at snowboard and ski combinations, and we did it a little bit with a more natural way of just coming up with combinations that worked, and we're right on the boundary, and that combinations that didn't work. In the next example, we are going to do it more mathematically, so starting by coming up with the linear inequality. You'll see what I mean by that as we go. So the first question here says, a banquet room, or this question says, a banquet room can hold a maximum of 144 people for a wedding. Each rectangular table seats 12 people and each circular table seats 8 people. You are hired to determine all of the combinations of rectangular and circular tables that can be used in the banquet room. So we just want to represent all the combinations that can be used in this banquet room. The variables that we're going to use, we have rectangular and circular tables. It is very useful to actually use meaningful variables. So we're going to let R equal the number of rectangular tables. And we're going to let C equal the number of circular tables. Now what we know here is that at each rectangular table there's 12 people, and at each circular table there's 8 people, and it's a maximum of 144. So the actual, when it says part B, you write a linear inequality. The actual inequality here is that 12 people for every rectangular table plus 8 people for every circular table has to be, because that's the maximum capacity, has to be less than or equal to, because it can equal 144. So that's the actual inequality. So we're going to represent that inequality on this graph. Okay, so I'm going to call the x-axis R. That's the number of rectangular tables, and the y-axis is going to be the number of circular tables. So we're going to come up with the boundary. So the starting point, as we've done with graphing all inequalities, is we're going to graph the boundary 12R plus 8C is equal to 144. So if I would like to find out the R-intercept, so in this case the R-intercept would be where C is equal to 0. So it would be 12 times R plus 8 times 0 equals 144, or 12R equals 144, and if we divide by the coefficient 12, we will get that R equals 12. So in this case, since this only goes up till 10, this axis, you may want to choose a different scale. In fact, I'm going to go up by 2s. So for the boundary, R is equal to 12. Okay, I'm going to find the C intercept next. So that would be is when R is equal to 0. So we have 12 times 0 plus 8C equals 144. So we have 8C is equal to 144, and if we divide by the coefficient 8, 144 divided by 8 is equal to 18. So again, if I go up by 2s, if I choose that scale, it will all fit here. Alright, so here is C is equal to 18. So what you can see is we actually have our boundary line in this particular case. So our boundary line, because the expressions are allowed to equal to each other, so because this is or equal to, that means that it's going to be a solid boundary line. So that boundary line is going to be solid. So there we go. So the last thing we want to do is determine which side of that boundary line represents all of the possible combinations of tables that they can have. Well, in this particular case, we can actually use the context of the problem to know which side it is. So is it possible, and we could try this side, which would be 0, 0, and we can even test it without even using the numbers if we want to. Is it possible to have a combination of 0 circular tables and 0 rectangular tables in the banquet hall? Is that allowed? Well, yes, it is, because that would hold 0 people, which is less than the maximum of 144. Or if you would like to, I could show you the test. So we're going to test 0, 0. Put it into here. So is 12 times 0 plus 8 times 0 less than or equal to 144? And the answer to that is definitely yes. So this entire side would be yes, which means this entire side would be no. So in this particular case, we would shade this side. Now a couple of pieces that I just want to add to here. So those represent all the possible combinations of rectangular and circular tables they could have in the banquet hall. So for example, they could have a combination of 4 rectangles and 6 circles, because 4 rectangular tables would hold a total of 48 people. 6 circular tables would hold a total of also 48 people, so that'd be 96 people, which they're allowed to do. So all of those combinations would work. The last thing that I will actually put in here is all of these. You can't have half of a table because they come as whole tables. All of these dots should be, or all of these integers should have dots on them, because we are restricted in this case to just whole numbers. You can't have negative amount of tables, and you can't have half tables, etc. So that actually represents all the possible combinations of tables that you could have in this banquet hall. Now if you're in my class, you'll try the following question and get me to look at it.